Okay, folks, time to start. Any announcements before we start properly?
I don't think are there any.
I don't think so either.
Right.
Yeah, just checking. You want to take lead?
Sure. So yesterday we had a look at our notion of typed expressions, and then we threw in an extra constructor corresponding to variables. So now our typed expressions, if you remember, they're not just indexed by the type that they have, but also by a list of types that are describing the types of all of the variables that are in scope. So if we take this list to be empty, we recover our closed expressions that we had until now. But if it's non-empty, then we can actually use the var constructor, and provided that we prove that the type we want is somewhere in the context, then by referring to the variable associated to that type, we can build an expression that has that type in that context. And prove that an element is somewhere in a list is given by this belongs or LM or whatever you want to call it inductive family, which has two constructors. Crucially, both of the constructors are talking about non-empty lists. Here you can see on the right, because it doesn't make sense to talk about, well, it makes sense to talk about an element being in the empty list. It just doesn't make sense to have a proof of such a statement. So you can always form such a statement. Not quite, there we go. So you could say 0 is in the empty list, but that would imply the absurd statement, and ACTA should be able, if I bring this definition into scope, to see that it's indeed impossible to have a proof of this kind of statement. So we have two constructors. Either the value we are looking for is at the head of the list, or it's further away, in which case we have an inductive proof here contained in the there constructor. So we can, for instance, say that 0 belongs to the lists that contains 0 and 0. And crucially here, if we do like the proof search, but asking for a list of the potential proofs, we can see that there are distinct proofs corresponding to either picking the first occurrence or the second occurrence. And that makes sense in our setting because we only have two types, right? We only have nat and bool, but we could have, say, 10 variables, and then necessarily there will be more than two variables that have the same type somewhere in the context. But they're still distinct variables, more or less. All right, so let's just pick the easiest proof, but there are other ones. And so then we can start writing expressions in a non-empty context. So let's say that I have a Boolean and I want to produce a term of type nat.
Why don't you name this example so you can evaluate it?
Oh, right, okay, yeah. What should I name it?
Example 1.
I was hoping to have something more insightful, but let's just call it example 1. So, of course, to showcase the new feature, I'm going to actually use this variable. So I said I have one variable of type bool in scope. I'm branching over that variable. So now I don't know whether the variable will be true or false, but I can still form that expression. And then in the true branch, I return 0. Oh, I cannot return 0. I have to wrap it. And then in the false branch, okay, let's do 1 and 0. And this is bool to nat. So the idea behind this thing, right, is that I'm converting the Boolean into the corresponding natural number 1 or 0. Okay. And then okay, let's have another example. I can do double. So let's be even more abstract. So you could say something like this, right? If whatever the context is, you know that there's a NAT somewhere, well, you can compute an expression of type NAT in that context. How do you do that? Well, you're saying, okay, if I name my variable x, and I want to compute x plus x as the name suggests, I can do add var x, var x. And so then whenever I want to use this double thing, I will need to provide a proof that NAT is somewhere in the context, which I should be able to do later on. Okay, so then we saw these typed expressions, and we just extended the evaluation function that we had so that it would also handle these sort of conditional expressions, right? These expressions only make sense if we can assign a meaning to all of the variables in scope. So this is exactly what Fred did with this definition, saying, what does it mean to have an environment for an existing context? Well, for any type, if this type belongs to gamma, then I have a value associated, a properly typed value associated to it. So for instance, I can write an environment for example, something like that, for this context. So with a view to evaluating this prior expression using that environment, right? So how do I build such a thing? Well, if I look at the definition, it's a function. So this, if I normalize this goal, it actually looks like an implication. So I can just introduce some of the arguments. Okay, that's not the best, but x is in gamma. So now I have x a type and a proof that x is somewhere in the environment. So I can case split on the proof, because if you remember, this belongs to symbol is defined as an inductive family. So when I get my hands on one of these, I can just take it apart to see how it was built. So if I do that, oops. Shouldn't have moved the cursor. If I case split on this expression, because this list only has one element in it, it cannot possibly be built using the there constructor, because it would mean I would have a proof that x belongs to the empty list, which is impossible. So Agda is just clever enough to see all of this and only gives me the one interesting case where x is now known to be bool, which means that this t-val of x also reduces to bool, and now I can just pass a literal. So I'll give true. I'll import true first, just the one, and I'll give it. So that's an example. Let's do maybe another one. So my nuts. So now I'll do one with two examples. So we have two natural numbers in scope.
Don't you throw in a Boolean as well? Yes, for fun.
Just in the middle. Yeah. Let's be crazy. Just Boolean in the middle. So now I'm going to inspect the proof. And it's going to tell me, well, if we're talking about the first variable, it has type nat, so I need to give a nat. Let's give 10. And then if I have a there, it just means the variable is somewhere further into the list, but I don't yet know which one of these it is. So I can do further splitting on the proof. And again, I have two cases. It's either at the head, which is the head of the tail, right? So it's a Boolean. I can give false this time, which will again create an import issue, and I can just throw it in. or it's even further away. And if it's even further away, now we're in the same position we were earlier when we only had a single bool. This will hopefully only give me the here case. Yeah, there we go. And now I can pick another natural number. So I'll pick 21. Okay.
So notice that our context here has three variables, right? The first one is a natural number, the second one is a Boolean, and the third one is a natural number. And to give an environment for this context, we have to give three values: a natural number, a Boolean, and a natural number, right? So we are saying, what is the value of each of these three variables?
Right. So then once we had our environments, we showed how to build the typed evaluation function extended for expressions that have a bunch of variables in scope. So if you remember the type of typed evaluation before we had a scope, we're saying that if you have a typed expression of type T, then you get a typed value of type T. And here it's the same. We make sure that now we have an environment for gamma to tackle the variables in gamma. So we always try to have these shared constraints between the various bits. Should I? I am tempted to break everything and just reorder this like this, because it might remind you of, okay, no, I need to fix everything, of something in the coursework, right? So we have a piece of syntax on as the first argument, and then I've added a bunch of parens to really give you an idea of what I mean. That just keeps fixing these things. I've missed one, of course. Right, so we have this piece of syntax here, and then its meaning as a function. So let's write it here. Syntax, meaning. And the meaning as a function is associating a meaning given to the variables, is taking a meaning given to the variables and transforming it into a meaning for the type of the expression. And so if you're thinking of the polynomials, when you're describing the meaning of a polynomial, you're saying, well, if you tell me the interpretation for the one variable, I will give you the interpretation for the overall expression that mentions that variable. So it's sort of a similar setup. And all of the cases were the same as in the usual typed eval, because these things are not actually relying on the variables. The only difference is that we're passing around the environments. And then in the var case, well, we designed our notion of environment precisely so that if we know that we have a variable in the environment, we get a typed value. So in a sense, we could have come up with this type just by writing this function and looking at what we needed here, right? If you look in this hole, we have a proof that T is in gamma, and whatever the definition of environment of gamma is, we want a typed value of type T. And then we define environment precisely as the thing that allows us to get it immediately. So that's also a good strategy. If you're not exactly sure what a definition should be, you can start implementing the function that depends on the definition and then look at what constraints are showing up and just verify that constraint directly as the definition. So then we're pushing the work to calling the function, which is where we need to define the environment. Okay, so examples. So we add bool to nat. So if I eval this with my bool, it should be equal to something. Of course, these are not in scope. All right, so here, the only thing I know from the type is that it should be a natural number, but there's a really strong constraint here. I said that this proof should be true by REFL, so I should be able to just solve the whole. If I solve with Control-C, Control-S, I get exactly the expression, because that's what REFL is saying, right? Things are equal to themselves. But I can actually insist on the thing being normalized by doing Control-U, Control-U, Control-C, Control-S, and I get 1, which is the expected thing, I guess. So if you remember, bool to nat is taking the variable and returning 1 if it's true and 0 if it's false. And the variable we've picked is exactly true. We could, of course, flip this bit, and then here we would get 0 instead. It's the right sort of behavior. And then we can have t eval double over my nats. And so if you remember, let's jump to the definition. Double was taking an arbitrary variable in scope that has type nat and returning the addition of it with itself. And here my nats was defining this environment with 2 natural numbers and a boolean in between. So if I am to pick a variable, I could say pick the first one, and that would give us 20. So 10 plus 10. The definition is here. Or I could pick the second one, which is the third variable. They're here. Oop. And then it would give us 21 plus 21, which is 42. All right. So I hope all of this is clear. And
out of tidiness, can you delete the second copy of the first example?
Ooh, how did that come in? Thank you. Okay. So now that we have these expressions, we're going to look at, well, in this case, it's an optimization, but in practice, in the coursework, it's any sort of syntax manipulating function you can implement, and then how to prove it correct with respect to the semantics. So I think the one we have is called like if full def or something. I don't know. So it's boop, boop, boop. Or maybe I could explain the motivation actually. So this bool to nat, in a sense, it's a real if then else. It's really branching over something we don't know yet, and then delivering a different outcome based on the result. But we also saw last week some boring ifs. So let's say it's a typed expression of gamma and whatever nat for whatever gamma we want. And it's doing like if then else of the bool true, then I'll return that 0, and then I'll return that 1. And users might write this in their code. This is really bad, but then again, sometimes people write really bad code. But more importantly, if you're thinking about your compiler, it will transform expressions, right? And so the codes that you end up manipulating might be really different from what the user wrote, because you merged some expressions, because you moved things around, etc. And something that was not written like this originally might eventually show up after enough transformations, just because of the way the code was restructured. And what you would like to do is make sure that all of these computation with outcome you already know are just gone by the time you're finished compiling. so that you do the work once at compile time and not every single time you actually run the program. So that's why we call it an optimization in this instance. So we want to get rid of these and the ones with just a literal false, and have them reduced just to the appropriate branch. So let's have a look at this. It will be a type and scope respecting function because the only thing it's doing is reducing these statically known branches. And well, I guess we can do everything slowly first. And B left, right. So if we have a variable, there's no like hidden if then else in there, so we can just get rid of it. If there's a natural number, it's the same. If there's a static boolean, it's the same. If we have an add constructor, then, well, it might be the case that one of the subtrees has a deeply nested boring if inside. So we are going to recursively, will it actually find this thing? Yes. So I can select the second one. Yes. And here it's the third one. Yeah, there we go. So I will recursively simplify the left branch and the right branch, and then there's nothing else to do but to put them together. Here in the if then else case, it's a bit different, right? So one strategy would be to look at B, and if it's a static boolean, then we would reduce that to either the left branch or the right branch. But actually, if it's an if then else inside, this might also be a boring if then else, which will reduce eventually to a constant value. So the right move is not to inspect the boolean we're given, but to inspect its simplification, so that you're already doing some cleanup, and that cleanup might reveal that this f, which looked complicated, is actually fully static. And once we have this intermediate thing, okay, maybe we only want to inspect, what's this? Oh no, I'm in caps lock. All right, so we're only interested in the case where the boolean is actually a literal, and in this case we can just branch over it. Oh, I should maybe literal B, using the semantic if then else. Need to reload. So yeah, looking at the scope, so this is a literal of a boolean, so this is an actual boolean which we can inspect to decide whether we're going left or right. And so if we are in this case, we're going to return a single branch, but we're not going to return it immediately because we haven't done any of the simplification. So it might be that the left branch or the right branch are themselves boring, right? So we're going to fold if L and fold if R, depending on whether we want to keep the left one or the right one. And if it's not a literal value, we will need to reconstruct a piece of syntax. So here it's static if then else, and here it's dynamic if then else. And again, here we need to do the cleanup on the branches, because even though this top level branching is not boring, there might be further boring ones later on. Okay, so this is hopefully correct. Maybe you can prove that it is. Oh, I should have inserted a mistake on purpose.
Okay, so how would we prove that this is correct? What do we mean by this being correct? Well, we want the optimization to not change the meaning of the expression, right? So we had this evaluation function which computed meanings for us. We wanted to say that, well, if I do this optimization, then I shouldn't change what the expression means. So it shouldn't be the case that by doing this fold if, then I'm changing something that used to evaluate to 17 to now evaluate to 42, for example, right? That would be a bad optimization. And you wouldn't be happy if your compiler did this to you, right? So you want your compiler to make things more efficient, but still computing the same results, right? So something like fold if correct should say that, so I'll copy the arguments of fold if to name this expression t, and then I would like to say that evaluating t should be the same thing as evaluating fold if of t, right? But evaluating something also takes an environment. So what again does it mean for this to be correct? Well, it should work no matter how instantiate the variables, right? So for every environment row, which is an environment for gamma, I guess. Put this on a new line. I want to try to show that if I evaluate t in row, I get the same result as if I evaluate fold if of t in row. Okay, let's see if the statement makes sense. Okay, it does. So then I can try to prove it. So I'm taking a bunch of arguments. Okay, and then my goal is exactly what we said, that evaluating t in row is the same as evaluating fold if of t in row, right? And how do I prove this? Well, it's the usual thing where this thing here is stuck because we don't know what t is. And fold if is stuck because we don't know what t is, right? So it's a very good idea to pattern match on t. So let's do that. Okay, and then we'll do the usual renaming. Try to use the same names as in the fold if up here. Okay, and then I just have to look at all of these different goals and see what happens, right? So in the variable case, our goal is easy because fold if is not touching the variable. So this will just become evaluation of the variable equals the evaluation of the variable, which was using this lookup. In any case, that will works. And fold if was not touching the literals either. So we would hope that these would be easy. They are. Okay, and then we had the addition case. So then what has happened here is that on the left-hand side, we were evaluating the addition, right? So that has turned into a real plus. On the right-hand side, we're evaluating the result of fold diffing the addition, which was still an addition, so that has turned into a real plus. And it looks like we can just get away with recursive calls on m and n, and that should do it, right? So try to just rewrite this row, see what happens after that. That made the first part line up nicely. I also rewrite the second bit. This. So I'm rewriting by these two things. And that made the second bit line up nicely. Or you could have used that to go back to this stage. Another way to do the same thing would be to notice that both sides really is pluses or something, right? So we could use a Kong of plus or Kong 2 to say, and then these would be our proofs that the sides are the same. But do it quick way for now. It's nice when it works, right? Okay, so this if then else, this is going to be the bit that's actually tricky, because this is where the fold if actually did something, right? So the first thing we need to do is we need to understand the goal. So what has happened? Well, the left-hand side, that's just the evaluation of the original expression. So that turned this syntactic if into a real if then else. Okay, fair enough. The right-hand side has this vertical bar in the goal. And this vertical bar is printed in the goal whenever the function is doing a with. So we see that our fold if did a with on this expression, and that's why we have a vertical bar and then that expression here. So this is saying that this whole thing here, or this thing within the brackets that has the vertical bar in it, is stuck because someone was doing a with on this expression. So we don't know what this is yet, just like before we didn't know what it was before we pattern matched on T, right? So the usual strategy to use in this situation is just like we were pattern matching on the same thing to get things unstuck, we should also do the with on the same thing to get things unstuck. So I'm going to do a with on the same thing as this. Okay, and then I look at my goal again. And now we see that the only thing that has changed is that, so there used to be an expression here, but now that has been abstracted to this P. So that means that I can now pattern match on the P, and that should make this whole thing reduce, hopefully. Try pattern match on P. Okay, and then I'll just rearrange things to be the same as up here. So up there, we first cared about the Boolean, this literal Boolean, and then everything else was a B prime, right? Okay, so let's look at this case first. So the thing that's nice now is that that strange vertical bar has disappeared, because we've done the same kind of pattern matching. So here we were doing a with on this, we're doing a with on the same thing. We were in the bool case, then this turned into an actual if then else. Here we are in the bool case, and we see that we have the same kind of if then else here, right? But we also see that these two things are not exactly the same yet. And why is that? Well, one problem is that we have lost the connection between the B and this Boolean LB, right? So we still have a B here. So that's not great. So we could pattern match on the LB, and that will get us a little bit into a better place, right? So now the right-hand side is simplified, but it should be the case that this thing was the same as the fold if of B, right? So I think we should retreat, and we should also do a with on the correctness for B. So,
Yeah, and this is a very general pattern, right? If you're currently proving something about any function f, and in that process you're abstracting over a call to f, you should immediately throw in also a recursive call to the correctness of that function f, so that you're always keeping all of your properties.
Because what happened now? Well, now we have this proof Q, which remembers the link between the LB and the evaluation of B, right? So if I now pattern match on Q, again, then this is looking much better. I mean, it's also still looking a bit scary, but at least now we kind of have the same ingredients on both sides of the equal sign, right? So here I have the evaluation of B, And then I have the evaluation of, well, L and versus the full diff of L. Right, so I think, so this thing, depending on what this is, should reduce to two different things, right? I wonder if I can just do a width on that here. To do that. Okay, and then I have this nested width thing again, so I'm just going to copy this here.
Yes, there are different strategies. Another thing you could see here is that on one side you have t-eval on the outside of an if then else, and on the left you have an if then else with t-eval in both branches. So you could also prove an auxiliary lemma telling you that you can push the t-eval through and distribute it into both branches, and then use equational reasoning to slowly rewrite one side into the other.
Okay,
like
so
both strategies work.
So I'm kind of inlining that proof here, which is usually not a good idea, but I think we'll get away with it this time. So now what has happened is we've abstracted the same thing on both sides, and it's a Boolean, so I can pattern match on it. I get two cases, and in this case, things compute like this. This looks like a recursive call to the correctness on R.
Auto, maybe even.
And in this case, it looks like a recursive call on the correctness of L, right? Solution found by Auto.
Oh, wow.
Okay. And then we have this case where we didn't actually do the simplification. Let's see what happens in this case. Right, so we see that, so we did the pattern matching on this expression and got this Boolean, and that's how we got rid of this vertical bar, right? But here, in this case, the vertical bar is still there. And the reason is that Agda doesn't know that it's B prime. It doesn't remember that we aren't in this case. This is a general pattern that what I did when I saw this was I commented out the cases Agda gave me, and I shouldn't have done that. I should have kept these cases. So in the meantime, I've expanded these.
Yeah, so to understand what's happening, Agda always checks every clause in isolation. It doesn't know what has been checked before. So when you're writing simple programs, you can just have a catch-all case that will handle all the other cases. When you're doing a proof, you need to be more specific, like say, it's not the first one because it's shaped differently that way, or this way, or this other way. Which is a bit noisy, but
right.
But these should be the easy cases. So
yeah, right. So we did a width on the full diff, and then in the meantime we inserted the correctness. So I've inserted the correctness here, and then again, this kind of looks horrible. Because Q, right, so the correctness says that this expression is actually the same as this expression. Let's do a nice way to do this.
Do you just want to do a ton of rewrites, maybe?
Yeah, but I don't think the rewrite will work here, right? But okay,
you should.
Okay, that's much nicer. Okay, and then what we did up here was we were still doing recursive calls on the left and the right, right? So I'll do the same kind of recursive calls here. Looks the same now, is that right? Yes. And here, I think it's the same horrible thing. So it's a little bit Yankee to get this right, but hopefully the high level idea is clear. So we do the same kind of pattern matching as in the function that did the optimization. And then we just have to do the same kind of with pattern matching as well and do the right kind of recursive calls in the right places. Right. What do you want to show them?
Yeah, I wanted to introduce some auxiliary definitions. Because Fred wrote this type as the notion of correctness, but you could actually split it up into sub-definitions to clarify what the ideas are, right? So the first thing I would say is that we had the definition not of propositional equality, which was equality of syntactic objects, but now a notion of semantic equality, right? We're saying, when is it the case that two expressions which live in the same scope and have the same type are equal, not just syntactically, but actually they mean the same thing. So we can introduce this definition here to be, well, T or S is equal to T precisely when, for all, for any environment assigning values to the variables they mention, then evaluating one is the same as evaluating the other. Oh, if I'm reusing the same one, that's not good. Can it infer this? Yes. So you can see that now it's not an equality about what they are, but how they behave, which is the right thing. And then you could say, well, I'm going to abstract away what it means for a transformation, a type and scope preserving transformation in general, to be correct. So let's say I have such a function, and I'm saying it's correct. F is correct. Whenever the original, forgot to, well, okay, let's call it transformation. Oh no. So what it means for a transformation to be correct, it's if you give me any term, it will be semantically equivalent to the transformed one according to this function. And then you can have full diff correct, literally be saying correct of full diff. So I don't know if we're doing any of this in the coursework, but quite often we will introduce these intermediary definitions just to make the core ideas more explicit. Another thing to notice, and that's going back to the full diff definition, maybe I can get both side by sides, is that if you look at it, if you stare at it, it's essentially like the t-eval definition, which is why you can actually prove the correctness, right? Because it behaves exactly the same, except that, so if you have a NAT, it returns a NAT, just like here you had a NAT, you return a NAT, a bool, you return the bool, and if then else, you return the actual if then else. So here you're doing it, but only if you statically know what the value of B is. So in a sense, you could have come up with this definition of full diff by looking at this thing here and saying, okay, well, what happens if I don't have the evaluation, if I don't have the environment? If I don't have the environment, the variable is stuck, so I just keep it. These things still compute to their appropriate values. And in the if then else, well, it will depend on whether this returns a stuck thing or a thing that can actually be fed to the if then else. And building on that idea, you can see that here we're preserving the addition constructor no matter what. But in the semantics here, we're actually using the semantic plus, which suggests that maybe we could do more than just folding the ifs that are statically known. Maybe we can fold the additions that are statically known. And if was a bit different because if is branching on exactly one value, the Boolean telling you whether you want to go left or right. But addition is actually taking two arguments, right? It's taking both the left-hand side and the right-hand side. And maybe there are extra simplifications you can throw in depending on whether one is a literal or the other is a literal or both of them are literals. So I think that might be something to do. So let's see, add, fold add, I guess. It will be a similar thing. Oh, I guess I should just define this. This would have been the smart move. Whoop. There we go. Pull set. Can I actually move this up here? This is a no. Transformation. And then I have fold add, which is another transformation. So maybe if you want to have fun by next week, you can try to implement these things that are internalizing some of the addition logic. And I think we're good for today. It's a good stopping point. Yeah, I don't know how to stop it.